Okay, here we are. We're going to review the material, and we're going to have our oral midterm on Thursday. And I just want to open it up for any questions which you might have concerning all of the material to this point, but especially the material that was given for the last homework, which will also be due Thursday. So let me open it up for questions. Let's go to the homework, and at least the homework that was assigned, and see if anybody has any questions about it. Okay, everybody can see my screen? Just nod. Okay, good. Okay, any questions about any of the homework?
I have a question about the test first. Is the stuff on the homework for Thursday also going to be on the test?
Yes, it is. That's the reason that I'm opening it up for questions today. The idea is to finish the chapter. I want to finish chapter 2, and so this will be a clean break. If we didn't include the stuff that was in the homework that was due on Thursday, then we'd kind of be breaking up the chapter. So it just seems like a very nice clean break. Okay.
Okay. Yeah. So I had a question then about the number 20, the Poisson Sum Formula. I went back and watched the lecture just to make sure I hadn't missed anything.
Yeah.
And we talked about it graphically, and what both sides of the equation mean.
Yes.
The formula means, and I understand like what the equation's doing and what's happening on both sides, but I don't necessarily understand how it applies to number 20.
Okay, number 20. What one has to do there is go to the book, and let me see if I can get the book up. And get well, I tell you what, it should be in the chapter 2 notes. So let me open up the chapter 2 notes. Okay, the secret here is to go to, oh my gosh, look at that. Okay, not this. This is the Fourier transform theorems. We want the Fourier transform pairs. So I'm looking on the left here. Here we go. So the question is looking at this, is there any place on here where one of the sides looks like the side that was given by the homework? And I think that probably this one's it, right? You see the e to the minus magnitude of t? And this has a Fourier transform, which looks a lot like what you were asked to do the homework about, right? So I think that if you take this Fourier transform pair, and by the way, it's even, so the Fourier dual is obtained simply by swapping the t and the u, which is very nice, since it's a nice even function. And I think given this Fourier transform pair, that you might be able to do that problem. Does that help, Aiden? Or would you like more elaboration? I can do more elaboration if you like.
Yeah, if I had some time to think about it, I might be able to figure it out. But I'm guessing that then you have to relate it to the Fourier series.
No, not well. It's the Poisson Sum Formula, is what you want.
Yeah, but the Fourier series is on the right side of that formula, right? So I figured.
No, not the Fourier series, but the Fourier transform. Wait, are you looking at the homework or the table?
The homework.
Oh, the homework. Okay, let me get back. Let me get back the homework here.
So this right here, what you gave us on the question, is then just a sample. It's just the Fourier transform sampled, right?
Yes.
And so, yeah, I'm still not really getting it.
Okay, well let's
not right this second, anyways.
Okay, let's look at the Poisson Sum Formula. Let's see if I can remember it. And I don't know if I can. Insert. I'm still getting used to equations on Google Docs here. I think the equation is that the sum over n of, you know what, instead of doing this, let me go over to, let me try this. Let me copy this and go over to the properties here over here and do a new slide. Now let's see if this works. Okay. That didn't work too good, did it? My cut and paste didn't do well at all. So I'm going to go back here and I'm going to do a, make it bigger. And do a print screen. And go back here. Do a, and then do a crop. Where'd my crop go?
The locusts.
I know it's, yeah, it's not very pretty. David, that was a terrible joke that took me a minute to get to you. Okay, there we go. Okay, so we have this here, and we want to apply it to the Poisson Sum Formula. Let me go see if I can grab the Poisson Sum Formula. Wait, I'm in chapter 5. I don't want to be in chapter 5. Okay, I guess I want to be in chapter 5. So let's go see if we can find the Poisson Sum Formula. I forget where it's at. Okay, that's the gamma function. It came after that. Wonder if I can do a search here. I can't do a search because all of my postings are cut and paste. Ta-da! Whoops. Okay, so there we have the question and the Poisson Sum Formula. No, I don't want ideas. Okay, so here's what we have. So this looks to be like this with t is equal to 0. In other words, t times the summation over n of x of t is equal to the summation over n of x of n over t. Is that okay? And so we have this, and I am going to set, oh boy, I want to set t is equal to 1. But what we decided was this was true.
Wait, I'm sorry. What, you set t equal to 0 first?
I'm sorry, I set, I'm sorry, I should have set Yes, this is the way it should be, nt. I'm sorry, this should be x of nt. So yeah, I set little t equal to 0. Does that clear it up? And I'm sorry I made that mistake. And I believe that we had this problem. So here's the point. If we substitute, if we set t is equal to 1 into this problem, we get the summation over n of e to the minus n, is that right? Is equal to the summation over n of 2 over 1 plus 2 pi u squared, or 2 pi n squared. Is that good? So what we have to do now is we have to evaluate this infinite summation. This infinite summation comes from the, is a special case of the geometric series. Let's recall the geometric series. Summation of, say, n is equal to 1 to infinity of, say, alpha to the n is equal to, if we call this a sum, and this, by the way, comes from high school, right? This is a geometric series. And I'm going to do n is equal to 0. You'll excuse me, n is equal to 0, so we have a 1 plus here. And I'm not going to go to infinity, I'm going to go to a capital N. So this goes to n. And we see that if we multiply this sum by alpha, we get alpha plus alpha squared. Hopefully you guys should have seen this in DSP at least. And so if we subtract this, if we subtract here from here, we get what? 1 minus alpha times the sum is equal to 1 minus alpha n plus 1. Right? Do you guys remember this at all? You ever seen it before? Maybe not. No? Okay.
I have no idea.
Okay. Okay, do you understand the summation that I'm doing?
That's supposed to be a G?
Oh boy. Okay, no, that's a script S for
Okay.
sum.
Okay.
Okay, so the sum, you know what? Let me kind of start over here because I was a little sloppy here. Okay, well, it's not let me erase it, so I'm going to have to start a new board here. Maybe it'll do this. Yeah, there it goes. Okay. Okay, in order to, well, okay, first of all, I think you can see that the summation of n, this is one that was erased, of e to the minus n is equal to, or has a Fourier is equal to, according to the Poisson Sum Formula, the sum over n of 2 over 1 plus 2 pi n squared. Is that okay?
Yeah, and so did you just choose capital T equals 1 because you knew it would give you what you wanted on the left, or what?
Yeah, this is what I want. This is what I got.
Okay.
To make what I want from what I got, I have to use t is equal to 1.
Okay.
So it wasn't anything of creation or being creative at all. It was just born out of necessity. Okay. So I want to point out this. This is equal to, this is an even sum. Isn't that right? Because the sum on the left is the same as the sum on the right. So this is equal to 2 times the summation of n is equal to 0 to infinity of e to the minus n. And I've counted the value at 0 twice in this, right? And folding it over. So I have to subtract off 1. I have to subtract off e to the 0. Is that okay? Okay, good. I'm getting some nods. This is good. There is the geometric series, and I'm not going to derive it. There's probably a few series that you should have under your belt. One of them is the geometric series. And that is the summation of n is equal to 0 to infinity of alpha to the n is equal to 1 over 1 minus alpha. Have you seen that series before? Maybe. This is only true. This is clearly not true for alpha is equal to 2, right? Otherwise, we'd have 1 plus 2 plus 4 plus 8 plus 16. That doesn't converge to anything finite. So you must have the magnitude of alpha is less than 1. And it works for complex numbers also. That's no problem. So minus 1 plus twice the summation I'm going to take this and I'm going to rewrite it like this. I'm going to write it as e to the minus 1 raised to the nth power. Is that okay? So that's equal to minus 1 plus 2 over 1 plus 1 minus e to the minus 1. So that's the summation. So the key here is, if you haven't seen it before, is this geometric series, which is a very, very important series. And with that, let me derive it for you, because I think it's probably important enough to derive, especially if you haven't seen it before. We're going to let S, that's supposed to be my script S, by the way, as equal to, and I'm going to subscript this with an n here, is the summation from n is equal to 1 to n of alpha to the n. Is that okay? Or n is equal to 0. Let's start at 0. So this is equal to 1 plus alpha plus dot, dot, dot. It's adding all these things up plus alpha to the n. Again, this is a geometric series. And if you multiply S sub n by alpha, you get alpha plus dot, 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 plus alpha to the n, plus alpha to the n plus 1. Is that right? And now what we're going to do is subtract these two. And you can see all of these things subtract and go to 0. And if we get 1 minus alpha S sub n, man, my n's are terrible here, aren't they? That's equal to 1 that's left over, and then over here is alpha to the n plus 1. And so the summation of n terms is equal to 1 minus alpha n plus 1 over 1 minus alpha. So this is the geometric series. Now, what we want to do is we want to let n go to infinity. If we let n go to infinity, notice that this goes to 0. This term goes to 0, but only if alpha is less than 1. Right? If you take 0.9 and raise it to the 1000th power, you get 0, basically, right? If you take 2 and raise it to the 1000th power, you don't get 0. So you better have it less than 1. So as n goes to infinity, the second term goes to 0, and we just have this 1 minus alpha, but under the condition that alpha must be less than 1. Strictly less than 1. Does it work for alpha is equal to 1? No, it doesn't work for alpha is equal to 1 because, yeah, no, let's just keep alpha is less than 1. And this is true as long as the magnitude of alpha is less than 1. So this is the geometric series. Probably if you're in the math version of electrical engineering, there's a few series you should have right off the top of your belt. One is the geometrical series, and the other one is the another one is the Taylor series. The Taylor series for e to the x. That's x to the n over n factorial. It's a good one to remember. Another one is the binomial expansion, which is that a plus b raised to the nth power. And you see this in binomial random variables quite a bit. Have you seen that? Ever seen that expansion before? Who knows what n choose k is?
Now that you say it that way, now that you read it, I think
Okay, you know what it means. Okay, so this is
better.
referred to as n choose k. N choose k, and the choose notation comes from probability. But these are three infinite series that I think people that are PhDs and electrical engineers should know. The Taylor series expansion for e to the x, the binomial expansion, and yeah, the Taylor series, the geometric series, and the binomial expansion. So Aiden, you were right. In the working of the problem, it was assumed that you did know what the geometric series was. So there were a few hoops to jump through. So that was the one that needed to be done. So hopefully, Aiden, does that answer your question to sufficient detail? Okay, thank you. Yeah.
I remember the version of the formula we used. I remember you called it a special case where we set t equal to 0.
Yes.
Lowercase t. We can just do that whenever it's convenient for us to use that form instead.
Yeah, exactly. What it is, it's one of the things in the toolkit that you have. It's this expression. It's this expression with little t set to 0. And if I could write straight, it's that. Sure. And it's applicable all the time. You know, it's applicable all the time. And the reason it's kind of cool is it relates in general samples, the sum of the samples that you have in the time domain with the sum of the samples that you have in the frequency domain if you're appropriately spaced. And that's, I think, interesting and occasionally useful. Go ahead. I'm sorry.
When we set t equal to 0, the negative sign in front of n and capital T went away.
Yes, it did, because, yeah, what Aiden has mentioned, if you set little t is equal to 0 here, you get t times the summation over n of x of minus nt, right? Is that what you were referring to? Well, here's the point. If you sum Well, let's see. What's the best way to explain it? Let me do it in a mathy way. Say you set n is equal to minus infinity to infinity. Now, let me give you an intuitive explanation, more of an intuitive explanation. If you have all, what's that?
Does it not matter? The negative sign not matter because when you flip it, the sum's the same either way?
It doesn't. It doesn't. Integrating from minus infinity to infinity means that you are starting at plus infinity and you're summing this way. So the way that we have it right now, you're summing this way. And I maintain that this is the same exact thing as doing the summation over m of x of nt, which corresponds to summing all of the terms this way. And it doesn't matter which way you sum them. If you sum them left to right or right to left, it doesn't matter. Now, interestingly, this does matter if you integrate, because you might remember that the integral from a to b is equal to minus the integral from b to a. So it doesn't work. It doesn't work in the integration, but it does work in summation. You don't have to worry about it. Okay, well, it's a good question, and it did require knowledge of the geometric series. So if you didn't have that in your background, that would have been a very difficult problem for you. So let's go back to the homework and see if you have any additional questions about it. Anybody get this one? This is reminiscent of the problem that we had to do with Dirac deltas, isn't it? Right?
Is it a trick question or is it as easy?
No, it's incredibly easy.
Okay, good.
Yeah, the result is a Kronecker delta at n minus 1. In fact, what I meant to put here, and I didn't do it, I meant to write n plus 1 in order to make it exactly like the other one that gave us so much problem with the Dirac deltas. But with the x sub n there, just the x sub n there, it turns out that's the identity operator of convolution. And you get the del of n minus 1 there. So that was my mistake. I meant the n plus 1. So, and this is exactly the same sort of problem that we saw before with the Dirac deltas. Okay, any additional questions or comments here?
Yeah, I had a question on number 19.
Number 19, okay.
So whenever you're trying to find the Fourier series of the twisted jink, I got kind of confused, I guess, in the trying to like go from calculating the C of n and stuff.
Oh, and things of that sort. Did anybody get this one, 19?
I used the Poisson Sum Formula.
Yes, exactly, yes.
And I wasn't sure if you just had to evaluate like the right side of the function and that's it. Like you just
and that's it.
Okay. Yeah.
Did you write it down? Is that something you could share with us, or?
I don't have it scanned, but it's on a piece of paper. And you know, I don't know how far you want us to go because my final answer does look kind of messy, but graphically it's really simple because it's only a 3-point summation. But
yeah, that's interesting, isn't it? Yeah, that is interesting. Yeah, the way that you do it, let me see if we can go back to here. I tell you guys, this is rough doing this. How come that doesn't grab everything? Anybody let me know how? Oh, there, that's cool. Okay. Ah, there we go. Okay. So what do we have? Aiden, what did you do? We had the, we had here the jink of t minus nt, right? Was it t minus nt or just minus n?
in capital T.
Okay, NT, thank you. Okay, well, this corresponds to this. So we know that this is equal to, if we take the t to the other side, 1 over t times the summation over n of x of nt e to the j 2 pi nt over t. I forgot my pi. And Justin, this is the Fourier series. There it is. That's a Fourier series. Now, of course, we have to figure out what the Jink Fourier transforms to. This is the x of t. And the Jink Fourier transforms to x of u. And I think that that was what, square root of 1 minus u squared
Yes.
times
And then-
pi of u over 2.
Yes, sir.
Okay. So that's what it corresponds to. So we need to evaluate this. And, you know, I didn't realize it when I assigned it, but this is incredibly simple, interesting problem. Because 1 minus u squared looks like a circle, right? From -1 to 1. And so this is the x of u. So what is x of nt? X of nt corresponds to samples of this. At intervals of what? 1 over t, right? Supposed to be arrows here. Let me try that again. What I meant to do is do arrows like this and say the separation between the points was 1 over t. Okay. Now, how many samples are there? Well, it depends on what t is, right? Because the bigger t is, the more samples you're going to be. But one of the interesting things about the Fourier transform of the Jink is that an infinite number of these samples are going to be 0, isn't it? So the Fourier series, as Aidan mentioned, is going to be finite. It's not going to go from -infinity to infinity. It's just going to be over a finite range corresponding to ever how many values a capital T lets in. Is that basically what you got, Aidan?
Yes, and so basically, because of the rectangle, the pi or the rectangle function,
Yes.
because of that, that's the reason why the summation only needs to be from -1 to 1, because no matter what your capital T is, you're only going to be in that range. Basically.
Sure. Yeah, you can do it two ways. You can look at the math and you can say, oh, this rectangle function prohibits me from sampling forever. But I like this geometric view, because this geometric view kind of plotting out what the Fourier transform looks like, I think it's readily apparent just from the little sketch that I've done here that most of the samples are going to be 0.
Yeah.
And I would suggest it works for me. I like drawing out pictures as much as I possibly can to help me visualize what's going on in these situations.
And then also, the rule for integrating a even function, or no, integrating an odd function from -a to a goes to 0. That applies to summations too as well. So if you know you're going to have, if you were to sum, let's say, a sine from -1 to 1,
Yes.
and so you can use that knowledge to help you with this problem too, and get rid of the j sine.
Yeah, you could. In other words, what you're saying is that since all of these coefficients are going to be even, all of these coefficients are going to be even, that we don't have to worry about the J sign part of this. So yes, that's true. So we could simplify this greatly. Which is I don't know, very interesting. Yeah, Aiden was making the point that if you have the summation from n is equal to, say, minus n to n of an odd function, that's going to be equal to 0, isn't it? Right? And the summation from n is equal to minus n to n, minus n to n of an even function is equal to the even function. You have to be careful here because you have the even function evaluated at 0. Notice that for an even function for a discrete time, we have all of the pairs between negative and positive, right? So we have this paired with this one, we have this paired with this one, but this 0 here, that doesn't have a pair. The value at the origin doesn't have a pair. So we must add twice times the summation, but from n is equal to 1 to n of even. Does that make sense? So we can take advantage of the similar properties of even and odd functions that we saw for continuous time and discrete time also. And what Aiden noticed was that this function is even. So when we sample this function with n over t, it's going to be even. This is going to be even. So therefore, if we're summing over symmetric intervals, then we don't need the J sign here because the J sign is going to just give us a 0 value. I hope that's clear. Okay, any additional questions? Let's go back to the homework.
I have a question about the discrete Fourier transform.
Okay, let's see which one is that. Yes, okay, for this one.
Yes, sir. So in the book, it mentioned that we assume that the left side of the equation for the transform is periodic, the xn.
Yes, it is.
Here it's not. So
the assumption is I'm giving you one period of the periodic function.
yes, but a to the n is not periodic.
Well, it is in the following sense. Let's go back over here. It is in the following sense. Forget this stuff. This is not applicable to it. A to the n means that, say, a is greater than 0. A to the n means it grows in a geometric sort of fashion, right? Maybe something like this. I don't know exactly. And this would have to be n minus 1. Let's see, I got to be careful here. I think it was from 0 to n minus 1. Let's see how I stated the problem here. Okay, see, it's a strict less than here, so it only goes up to n minus 1. So I can talk about a sub n here going up to n minus 1. Man, that's the worst one in the world. Goes up to n minus 1. And then by periodic, I mean that at n, which is the next place, it starts over again. And it's periodic over here too. So does that hopefully clears things up, right? I'm giving you one period of the periodic function. I'm saying in that period, it's equal to a to the n.
So basically, we need to derive a general expression for the DFT for any given period, basically?
Well, what one has to do is go to the definition of the DFT. Let's go through this. Let's see, I keep forgetting, I believe this is a plus. That's the DFT, right? And we can write this for the problem that we have as the following. Correct? And guess who our old friend comes back to? This should be n minus 1. Our old friend, the geometric series, comes back to play. Is that okay?
Yes.
And therefore, you remember our geometric series. This is this summation that I did before. Summation of n is equal to 0 to n minus 1 of alpha to the n. Now, this summation had no requirement for alpha. Alpha could be 5,000. It doesn't have to be less than 1. Only when n goes to infinity do we require the magnitude of alpha to be less than 1. But here, no matter what it is, whatever it is, the value is correct. And I believe it's 1 minus alpha to the n minus 1. Or is it the n plus 1? I think it's n plus 1 over 1 minus alpha, right? So this summation, the DFT, is equal to 1 minus a e to the j 2 pi k. I'm running out of board space here, gentlemen, so I'm going to, let's see, I'm going to try to maybe get board space. So it's 1 minus, I'm just going to do this, n plus 1 over 1 minus this, where the parentheses include this term. So if you took this term and stuck it in here, that's what the DFT would be. Does that make sense?
Yes. And so for the geometric series, you said there was two different, basically there's two different series depending on your restrictions on alpha. Is that what you said?
No, let's see if I have the notes that I had from before. Yeah, here was the geometric series. The first one was this. This is a summation from n is equal to 0 to n of alpha to the k. This applies if alpha is equal to 1,000 or 1,000,000,000. Okay, it doesn't matter what it is. And the answer is this. And that's always true. Alpha can be any number that we want. The sensitivity comes in when we set n going to infinity. Because if n goes to infinity, we have to make sure that this term goes to 0. This term goes to 0 only when alpha is strictly less than 1. So there's only one case. The one case is the finite sum, and a special case of that is when n goes to infinity. And then it has to, then we have to assure that the magnitude of alpha is less than 1. Otherwise, the series diverges. It begins to blow up, right? So anytime you have a finite sum in a geometric series, it's a closed form solution. It's something that you can write down. But if you have an infinite number in your series for a geometric series, you have to make sure that whatever you're raising to that nth power is strictly less than 1. Otherwise, again, the series diverges. Okay, these are all great questions. Any other questions? Let's go back to the homework.
I got stuck with number 18.
Oh, number
I tried
18.
I tried a couple of things, but I was not able to finish.
Okay, did anybody get 18 that can share it? Okay, David, I'm going to give you screen sharing capabilities here. Glauco, you're at Starbucks. I see Starbucks behind you. Are they closed? Is Starbucks closed? I can't hear you. Oh, it looks like they're closed. Okay.
Yes. No, I was in the class with Dr. Schubert, but when the class finished, they make me move out. So I'm here now.
So you're
He said,
you're a man without a room, huh?
yeah.
Okay.
He told me to say to you hello, Dr. Schubert.
Oh, okay. Dr. Schubert and I are great friends. He's I have a lot of respect for him. Did you know, you guys that know Dr. Schubert, you know he's an ordained pastor, and that before coming to Baylor, he was a full-time professor at Cal Poly, I believe it was, and he was the main pastor at a very small church, very small Baptist church that he led. So he's a smart guy, not only in engineering but in scriptural matters. A lot smarter than I am. Okay, David, you need to share your screen here.
Okay. I can't share by means of my screen, so sorry.
Okay, so you can't do
Right
it
now.
then. Okay. Well, we gave it a try, right? Okay, so let's get back to Glauco's question, and I'm going to share my screen again. And we'll get back to the question. You had a challenge with this one. Anybody else? Can you describe it? I think that the way you can actually describe this very easily. Anybody get this at all? Besides David? Okay. Well, let's put on another new slide here. Here's the key. E to the minus pi t squared. And this is a beautiful Fourier transform pair. Hello, everybody. It looks like I dropped off.
Oh, now we can hear you.
Okay, I hope that was temporary. Again, if I drop off, simply wait, and I'm going to switch to my cell phone hotspot, which apparently works well also. Okay, let me give this a try here, and go to. By the way, I just ordered a new Wi-Fi service, so hopefully that should come into play and help us out a little bit. So this is true. E to the minus pi t squared Fourier transforms to e to the minus pi u squared. A beautiful, beautiful Fourier transform pair. Very, very easy to remember. So if we have an e to the alpha, this is kind of our x of t, if you will. If we have a x of at, hold on one second. Oh gosh. I have distractions in my house. Okay, if we have x of at is equal to e to the minus pi at squared, right? We know that this Fourier transforms by the scaling theorem to 1 over the magnitude of a times e to the minus
Dr.
pi.
Marks?
Yes. Am I breaking up?
No, I don't know if you're trying to share your screen.
Oh, I'm
but
not sharing my
not
screen. I'm
seeing
sorry.
anything.
Well, silly me. Okay. Thank you for letting me know. Okay, we good? Okay. So here's what I said. This is the beautiful Fourier transform here, right? And if we said x of at is equal to this, we know that the Fourier transform is this, right? Correct? So so we know that e to the minus pi b squared, and I forget exactly how I phrased it in the homework problem, but this is equal to e to the minus pi u over b squared, right? And let's call this y, or no, let's call it h of t, h of at, hat. So then that we know that when we convolve in one domain, what do we do in the other domain? Everybody said multiply.
Actually, I'm not quite sure I catch. I follow the second line.
Well, the second line is exact. You mean this line?
No, the line above that, or
Oh,
well, that
well,
and the line above it.
okay,
Because
these are Fourier transforms pairs, right?
yeah,
Okay, so x of at corresponds to this, and we know by the scaling theorem that this is equal to 1 over the magnitude of a times x of u over a. That's the scaling theorem, right? Do you agree with this? That this
yeah.
Fourier transforms to this.
Mm-hmm.
So that means,
right.
so that means
But if you use,
say again?
but if you're using the scaling theorem, wouldn't it be a squared?
Oh, you're exactly right. Silly me. Yes, you're exactly right. Thank you. Thank you, Aiden. That would be a squared. Okay, is that better? So therefore, we would have now the convolution of this would be equal to the product of their Fourier transforms, which look to be 1 over a squared, plus 1 over b squared, times u squared, right? Did I get that right? Wow, no motion in the peanut gallery. You guys
Yeah,
don't
but our homework problem doesn't give us the coefficients being squared. So does that change? Doesn't that change something?
oh, okay. You're right. You're right. My bad. Okay, let's start over again. X of t, okay, equals e to the minus pi t squared. Let me get it right this time. You give me enough time, I'll get it right, gentlemen. So we have this, and then x of Okay, you tell me what I should put here. How about square root of A? Is that okay?
Yes, please.
Okay, and I apologize for this. So this Fourier transforms to 1 over the square root of A times x of u over the square root of A, which in our case would be 1 over the square root of A times e to the minus pi times what? U over the square root of A squared. Is that better? Thank you for correcting me, by the way. So h of square root of b times t is exactly the same thing, except that it's a b, right? So if we have the convolution of these, then that's the product. You know what? I'm going to try to put this on a single line because I'm going to run out of board here pretty soon. That's equal to 1 over square root of AB times e to the minus pi. And then I'm going to get 1 over A plus 1 over B times u squared, right? Now what this is this is equal to 1 over the square root of B, square root of AB, times e to the minus alpha, minus pi, and I'm not going to work the thing out because I've run out of space here, but this is equal to be minus pi times e to the minus pi alpha u squared. Do you agree with that? Where alpha is equal to 1 over A plus 1 over B. Now here's the question, not working it all the way. Can you inverse Fourier transform this? The answer is yes, because all you do is you go back to here and apply the scaling theorem going back the other way.
Wait, isn't alpha the square root of 1 over A plus 1 over B?
No, because alpha, yes, David, okay. Thank you. And even though any tone in my voice that showed disgust was disgust with me, okay? So yeah, it would be a square root of 1 over A plus 1 over B. But here's the question, given this and this Fourier transform pair that we started with, can you go back and compute the inverse Fourier transform? But here's the interesting part. The interesting part, if we step back at this, we can work in the details and get all the constants right and things like this. But a Gaussian convolved with a Gaussian is a Gaussian. That's an interesting, I think, an interesting property. And a Gaussian convolved with a Gaussian is a Gaussian. Now here's something. If you take my course in random processes and noise, you'll find out. And we're not going to do this in this class, but you take any functions, you take 1,000 functions, arbitrary, and they all have finite energy, and you convolve them together, guess what you get? A Gaussian. It doesn't matter. It doesn't matter what the functions are. I mean, you think of a rectangle, for example. This is just a side. This is not part of this course. If you convolve a rectangle with a rectangle, what do you get?
Triangle.
Yeah, you get one of these, right? What if you take one of these and you convolve it with another rectangle? Convolve it with another rectangle. What do you get? You get a piecewise quadratic. You get. Guess what? It's already starting to look like a Gaussian. And if you keep convolving it with a rectangle, you'll get another Gaussian. Now, there's exceptions, of course, but just about any functions that you convolve with themselves will end up a Gaussian. You can take like a one-sided exponential like this, and you convolve it with itself a million times, you get a Gaussian. Everything Gaussian is really a strange animal in that it is the end product of endless convolutions, no matter what you do. So it's a fascinating process. And anyway, what we've shown here is that a Gaussian, and this is kind of the takeaway that I wanted from the problem, is a Gaussian convolved with a Gaussian is equal to a Gaussian. That's really interesting. Now, the parameters on the Gaussian are going to change. If you convolved one Gaussian with another Gaussian, you're going to get a third Gaussian, but that third Gaussian is going to have a variance, or it's going to be spread out more than any of the first Gaussians are. Because convolution, if you think about it, is typically a spreading sort of operation. It takes functions and spreads them apart if you convolve normal functions with themselves. Okay? Any other questions then? Did this answer the question okay, Glauco?
Yes, yes. The last change of variable was what I was missing. Thank you.
Okay, thank you. Thank you, thank you. And just in my defense, the problem I was working up here was right. It's just not the problem that I assigned to you. So sorry about that. Okay, any additional questions about the homework? We'll go back to the homework here. We have a few more minutes. That was a long pause after your David.
Yeah, I was wondering if we'd gone over discrete time convolution, and then I remembered that we had.
Okay, yes, we have. We have. It's just like continuous time. Here's the thing, guys. This is supposed to be a review, and I'm hoping you've all had at undergraduates a little bit of DSP, a little bit of Fourier analysis, and so hopefully this is a review.
A quick question about the frequency response. So when we were talking about it, you used mu, I think you called it. It looked like a V. And that's because when you do the frequency response, you're only evaluating at one frequency, right? And so that's why you wouldn't use U, because you're not using the whole range of frequencies.
Well, you mean for the discrete time Fourier transform? Is that what you're talking about?
No, for the frequency response, the LTI frequency response theorem.
Oh, okay. No, my entire point is with that. Let me get a new response a new slide here. But the beautiful thing that we've shown in linear analysis, and this is the reason that we use LTI systems, is that if you have an LTI system and you put in a frequency with a frequency of nu, you're going to get out something exactly with that frequency. But it's going to have a different magnitude and different phase. And the magnitude and phase are kept track of by h of nu. And this is one thing that we need to be careful of. We think that we're really great in Fourier analysis and systems theory, but this only applies to LTI systems. one of the questions that I've asked on PhD qualifying exams is, what is the impedance of a diode? And oftentimes the students will go here, oh, impedance of a diode. What's the impedance of a diode? Impedance, of course, is the ratio between two phasors. And phasors are only meaningful in measuring relative magnitude and phases of things. If you have a nonlinear device such as an ideal diode doesn't have any frequency response. The whole concept is not applicable there, because with a diode, like for a full wave rectifier, you put in a sinusoid, and if you have a half wave rectifier, for example, what do you get out? You get out something like this. And so no longer is it just a frequency of nu, it's a frequency of nu and all of its harmonics, right? Because you've chopped off the negative frequencies. So we're very limited in application of LTI sorts of systems. And anytime you have a nonlinearity, you have to go away from LTI systems into there's a generalization of system analysis called Volterra Series, and that is applicable sometimes. Dr. Bayless's group, as Adam knows and Justin knows, is something that we go into nonlinear systems all the time. We haven't used Volterra Series very much, but that's the generalization of the LTI system to nonlinear systems. But even there, it's to mild nonlinearities. You can't have cattywampus nonlinearities and apply Volterra Series, but there is an extension here. But that's important to remember, that the LTI system assumption is very applicable, and there's lots of places we can use it, but it can't be applied universally. It can't be applied to nonlinear systems. It can't be applied to time variant systems. A system, for example, if you have a circuit with a resistor whose ambient time changes with respect to temperature, you cannot really talk about the frequency response over an interval of time, because the frequency response keeps changing. So it has to be both linear and time invariant. So if it's nonlinear or time variant, you got a problem. You got to go back and scratch your head and look what the applicable theory is. Did that answer the question, Aiden?
No, my question was more about the theorem, the actual equation. Like, we had an x to t convolved with e to the j 2 pi mu t equals.
Yes.
Yeah, I was talking about that equation. So when you have mu, like if I had an actual value for mu, like it would be one specific frequency, right, that I'm testing with my system, basically.
Exactly. In fact, this sinusoid, which we're putting in here, I'm talking about is e to the j 2 pi nu t.
Yeah. Okay. And so, yeah, when I came back and looked at it, I was wondering why we didn't use u, and I rewatched the lecture, and I got the impression that it's because it's a single frequency.
It's a single frequency, yes.
Yeah.
But the thing is that the output of this, of course, is h of nu, e to the j 2 pi nu t. In other words, same exact frequency, but with a different magnitude and phase, right?
Yeah.
So that's what the output. But the thing is that, yeah, we're visualizing this through a specific experiment. But this same thing happens for a number of frequencies. And if we were to look at u and we were to plot out different values of nu, and we did it for all nus, we would literally carve out the frequency response h of u. So we're getting the frequency response 1 point at a time. We're getting the frequency response 1 point at a time. Now, of course, as I mentioned in lecture, this would take one heck of a long time. It's easier to hit the system with a delta function. Why a delta function? Because a delta function has a Fourier transform of what? 1. So therefore, all frequencies are in that delta function. Every frequency in the world is in that delta function. It has a Fourier transform of 1. And so you put it into this LTI system. And because all of the frequencies are there, it turns out that the result, which is the impulse response, is takes into account all of the different frequencies, because all of the different frequencies were imposed. And of course, we know that the frequency response, I'm sorry, that the impulse response has a Fourier transform of the frequency response of the system. And this is a lot easier way to get the frequency response than measuring them one at a time, but the math is exactly the same. It's just different approaches to getting the same result. Did that clear it up, Aiden?
Yes, thank you.
Okay, very good. Any additional questions on this? Okay, that being the case, then I think that we're done. And yeah, oh boy, David, I just about closed the door and you stick your foot in, and I don't get it closed. Okay, go ahead.
What does it mean to square the discrete Fourier transform and inverse Fourier transform?
Oh, yeah, yeah. What I mean by that. Here's what I was trying to get. I was trying to get you to do a discrete Fourier transform or a discrete convolution here. The idea is that if you have x sub n, and I think this is a DFT problem, right? And so it has a Fourier transform, a DFT, that is x of k, right? What I wanted you to do is I wanted you to square this x sub k. And what we know is that this is going to inverse Fourier transforms to the convolution of x with itself, right? Except that if it's a DFT and you don't zero pad, this is going to be a circular convolution. So I can even draw a circle around the convolution sign to denote a circular convolution. So that's what I mean by squaring the transform. I just want to get back to the DFT convolve with itself. I wanted to give you something where you did circular convolution, and this is the easy example that I could think of.
All right, thanks.
Okay, any additional questions? Okay, let's see. If there's no additional questions, we'll see you Thursday then for the examination.